Hello, this is Matthew Valenti, and today's lesson in wireless networking is on the topic of free space path loss. You can find this information in section 1.2 of the Wireless Networking Handbook, which is available on my webpage. Okay, so here's the problem we're going to deal with today. Suppose we have a transmitter, TX, and that transmitter is separated from a receiver, RX, by a distance of d. We'll assume SI units, so our distance is in units of meters. Well, the transmitter transmits with a certain energy or power, and let's let the transmit power be denoted PT, and that would be in units of watts. Now, sometimes with an RF signal, a watt is a fairly large value, so we might actually denote it as MW for milliwatts. Now, the receiver, it receives a power PR, and of course that would be in the same unit. It could be in W or it could be in milliwatts. Now, what we want to do is we want to relate the receive power to the transmit power. And of course, they're going to be related through the distance, but they're also related through the wavelength, lambda. So this is the wavelength of the RF signal. It would be in units of meters. Now, sometimes you might actually not have the signal specified as a wavelength, but it might actually be specified as a frequency, F. And then as a frequency, it would be specified in hertz. Now we know that lambda and F are related in so much as lambda times F is equal to C, where C is the speed of light, and the speed of light has a value of approximately 3 times 10 to the 8th meters per second. Okay, so of course if we were given the problem, let's say maybe as a frequency instead of a wavelength, then we can easily find the wavelength by simply taking the speed of light and dividing by the frequency. Lambda equals C divided by F. Okay, so now let's think about how the signal propagates from the transmitter to the receiver. You have this wave front that starts at the transmitter and it goes towards the receiver. And one way to think of this wavefront is as if it were a bubble, a sphere, if you will. And so we have here a sphere, and the sphere's radius is equal to the distance between the transmit antenna and the receive antenna. So initially, of course, this bubble is going to be fairly small, because the transmit antenna is an isotropic antenna. It's just a point source, and it propagates signals equally well in all directions. As time progresses, the wavefront is going to get bigger and bigger until this bubble size, or radius, is equal to the distance between the transmitter and the receiver. Okay? Now, what we have on the surface of this bubble is we have all of the energy, or all of the power that's being transmitted. So we have a power of PT that is equally spread out on the surface area. But the antenna only receives a certain small portion of that energy, of that power. And the amount of power that it receives is proportional to the effective aperture, the effective area of the antenna. So now let's think about the amount of power which is captured by the receive antenna. And we're going to call that PR. And the amount of power captured by the receive antenna is a function of two quantities. The first quantity is the effective area of the antenna. So that would be in meter squared. So that is the amount of area, or the amount of area of the energy which is captured by the antenna. It's a physical quantity. The actual value is going to depend some on the electrical characteristics of the antenna. And then we also have this quantity phi, which is called the power flux density. Okay, and that's just a fancy word, but really what it is it's the amount of energy per, or power per unit area sitting on the surface of this sphere. So basically we have the sphere here, and a part of it is, part of this area corresponds to the antenna, and so we have this total area of the sphere, but only a very small fraction of that surface area has energy which is actually received by the antenna. And so it depends on the effective area of the antenna as to how much energy is actually captured by the antenna. Okay, so this power density phi then is equal to the total power transmitted divided by the surface area. Total area transmitted being PT. Energy has to be conserved, so this energy is not absorbed by anything. So out at distance d, the amount of energy around this entire sphere sitting on the surface area of the sphere still has to be equal to PT. Divide that by the area of the sphere, which is 4 pi d squared, d being the radius of the square. D is actually distance, so think of the transmitter being at the center of the sphere and then the receiver being out on the surface of the sphere. So the distance from the center to the surface, of course, is d, which is the distance. So don't think of it as being a diameter. It's actually a radius. There's actually distance is what we're using d for. And so that's the power density. That would be in units of watts per meter squared. And then if we take this power flux density and substitute it into our equation above, then what are we going to get? Well, we're going to get something that looks like this. Okay, so at this point we actually have an equation, but most of the time the antennas are not specified in terms of an area, but instead they're specified in terms of a gain, G. And gain and area are related. Gain is 4 pi AE divided by lambda squared. Okay, basic equation. We won't derive it. There's a derivation in the Rappaport textbook if you really want to see it. But this basically shows how antenna gain is related to the effective area of the antenna. Let's solve for AE, and then AE is equal to lambda squared G divided by 4 pi. Okay, so let's take this quantity here, and what we're going to do is we're going to go ahead and substitute it for the value of AE. And there we go. Oh, wait, I should probably erase this AE, and then we're going to go ahead and substitute in this value right there. We could do a little bit of bookkeeping, PR, and make it a function of, let's go ahead and put together anything that's squared. So we got our lambda, there's 2 4 pi's in that equation, and a d, and this whole thing is squared. And then we have our G and our PT. Now this G actually is the gain of the receive antenna. And if we also have a transmit antenna gain, so it's not isotropic, we actually need to account for that. So there's our TX antenna gain. You just kind of throw it in there. And finally, if there's any sort of a loss, L, we can put that in the denominator. And so there we go. We now have an equation for free space path law, which says receive power, lambda over 4 pi d quantity squared, GR, which is the receive antenna gain, PT, GT, which is the transmit antenna gain, divided by L. And we're done.